Mohammed Hamid, and today I will be presenting the paper integrating post-quantum secure encryption in operating systems kernel and its networking stack. Uh, so let's get started. Starting with the motivation behind me choosing this topic of integrating post-quantum secure encryption in operating systems kernel and networking stack. So the reason that I selected this topic is because of the two seminars that I attended at NYU Tandon. Uh, One was by Matthias Troyer himself. So you must be aware, Matthias Troyer is the vice president of quantum computing at Microsoft. His work there has been phenomenal. I have been following his work for quite some time, and when I got an opportunity to attend one of his lectures, I was just thrilled. And during this seminar, Matthias Troyer was explaining how quantum computing works and how using quantum computers we will be able to solve computation problems in just a few minutes, which might otherwise take several years on traditional computing. And at the end of the seminar, one of the professors at NYU Center for Cybersecurity asked Mr. Troyer that what will happen to the existing cryptography and encryption if quantum computing becomes easily accessible. And it was then that I started realizing that not only do we have to think about compute, we'll have to think about security as well. Uh, and the second seminar that motivated me in pursuing this topic was the one conducted by Center of Cybersecurity again. It was called AI and Ethics in Cybersecurity, and it was just held a few days before we had to make a submission for our papers in operating systems. And in this seminar, we discussed the panels discuss in great detail how cybersecurity needs to catch up with the evolving AI world and how security has to be more enhanced to counter to the most sophisticated AI-enabled attacks. And in this seminar, again, this topic of threats to infrastructures was raised by quantum computers, and panel did agree that not only do we have to protect our infrastructure against AI, but we'll also have to protect our existing infrastructure from the quantum computers as well, as it might become easily accessible over the next few years. And in fact, I went to one of the panel members at the end of the seminar, and I did actually ask her that, I was deeply interested in quantum secure encryption, and I have a paper to propose in the upcoming operating systems course, and what does she recommend? And she did say me that I should explore this topic of, how operating systems can be made more enhanced for a quantum secure world. And she actually said that there's a company that is already doing it. It was called Crypt, and I did look into this startup. It's a startup, but they have been able to gain many Fortune 500 clients because of the work that they are doing. And I've found this to be quite a cool company that they're making their existing infrastructures quantum secure. In fact, I did apply for a job at this company. So these were the two personal motivating seminars for me that led me to choose this topic. The other motivating factors behind me choosing this topic is because, as we are aware, uh, it is possible that in the coming few years, quantum computers will be easily accessible for large organizations and governments. And this poses a very unique threat called harvest now and decrypt later. In these kind of attacks, the adversaries may be already collecting a lot of data now, and as we are aware, storage is cheap. And once quantum computers becomes economically viable to access, these adversaries can go ahead and decrypt this data. So this is the other motivating factor. The last being operating systems are most poised to solve this issue. And we need to have this as core capability in the operating system and not just an additional add-on. Uh, so moving on to the hypothesis, I propose this hypothesis in two parts. One being very recently, in fact, it was in August 2024 that NIST and IETF, NIST being National Institutes of Standards and Technology, and Internet Engineering and Task Force sat together to standardized three post quantum encryption standards, and the aim is to be able to integrate these post quantum encryption standards in operating systems kernel and networking stack. And this is just one part of the hypothesis. The other being, the applications should be able to seamlessly select between traditional cryptography and post quantum encryption. And this should be very seamless so as to allow backward compatibility and ensure that there's not an increased load on the machines or compute. Obviously, a lot of research has happened in this area already. But what I've seen during my research is all this research that has been done in this field has happened in isolation. So, for example, these are the three papers that I referred extensively for this paper presentation. Uh, the one by Chawla and others, they focused about implementing quantum secure encryption at the network layer, while Revati and Sugandhi tried to implement this quantum secure encryption at the application layer, while Leo and Moody tried to standardize some post quantum cryptographic algorithms. While moving on to the implementation part, how will we go about implementing this integration of integrating post quantum standards in the existing operating systems kernel and networking stack? So to be able to do this, we can just make use of the two of the three standards proposed by NIST and IETF. Uh, at a very high level, we can use MLKEM for key exchange and MLDSA for digital signatures, and these can directly be embedded inside Linux existing security infrastructure. So, for example, MLDSA can be used alongside the classical encryption algorithms like RSA. And if we talk about the network side, we will have to extend TLS to support MLKEM as well. And this will allow applications to choose between traditional cryptography or quantum cryptography. Uh, so to be able to do this and verify our results, let's talk about the test bed setup. Let's assume that we have an operating system, in this case, a Linux operating systems with the proposed post quantum encryption standards integrated already, and we are running this Linux on a multi-core processor, and we are running it for an enterprise workload. And I've chosen a number 500, in which 500 is the number of concurrent applications running at the same time. And of these 500 applications, let's assume that 70% of the applications are not so sensitive, and they should be fine with just traditional cryptography, while 30% may contain some sensitive while 30% of the applications may be dealing with some sensitive data, and these will require quantum resistant protection. And we are going to evaluate our setup in three configurations. One being a very baseline traditional cryptography like RSA 2048. The other being all the applications are being encrypted by a pure in the pure POQC mode using only quantum secure algorithms. And the most importantly, a third configuration, which is a hybrid mode in which applications can choose between a traditional cryptography or a quantum secure cryptography. So, so let's go ahead. Let's see what is the metrics that I have chosen. So I decided to choose signal generation and verification time for all of the OS operation processes, and uh, measured processes like authentication, kernel code, module signing, inter-process communications, and had to do it for over 1,000 operations to be able to achieve some significant number of time, because these processes finish quickly and we have to run over a large number of iterations to be able to measure it. Uh, Moving on to the results of these experiments. So here are the results. So as you can see in traditional cryptography, it took around zero point 0.5 milliseconds for verification time and zero point 0.8 milliseconds for generation time. While in the case of a pure quantum secure cryptography, in which all the applications were uh, all the applications were used were protected using quantum secure cryptography. It took a significantly huge amount of time. Like it took around 1.1 milliseconds for verification time and around 1.45 milliseconds for generation time. While, as expected, if we choose a hybrid approach in which quantum secure applications choose quantum secure cryptography, and applications which are not so sensitive, they can go ahead with the traditional cryptography. In such a kind of hybrid setup, it took around zero point 0.8 milliseconds for verification time and 1.2 millisecond over generation time. And obviously, this will still take more time than the traditional cryptography. But the jump here from let's say in case of verification time, it's around 60% jump. Uh, and in case of a generation time, it's a 50%. Hybrid mode is taking 50% more time. But if we compare to a pure PQC mode, this is significantly higher. Uh, I think it is, let's say, I have written some numbers here. I think for verification time it is 120% slower than traditional, and roughly 80% slower than traditional generation time. So I believe anything that goes beyond 80s and more than 100% is very slow to be acceptable. But if we are keeping those numbers lesser than 100%, somewhere around 50 to 60, I believe it is still acceptable if we are ensuring that those sensitive applications are quantum secure. So these are some of the results that I have added it here for the reference. And so what are the next steps? So obviously the next steps is to be able to reduce this latency from 50 to 60% to something even lower. And then we should be able to ensure that there's no administrator misconfiguration